Hello, today I'm going to show you how to make a fairly precise average temperature drift measurement on an oscillator circuit. You can see here we have our clock circuit. The scope is measuring a nominal frequency of 5 megahertz. You can see our trigger point is on the rising edge of the clock. And so what we have here, what I'm probing is a standard Pierce oscillator circuit with a ceramic resonator set up as a 5 megahertz oscillator. That gives us a 200 nanosecond period on the waveform, which is what we see here on the scope. Now I'm going to adjust the time base of the scope so that I can easily make large delays in the displayed area of the waveform. I'm going to delay out here to about 10 milliseconds. So you can see here we're delayed 10 milliseconds from that trigger point, and now we're going to expand the clock back down to where we can resolve each clock edge. We'll set it here at 100 nanoseconds per division. So you can see we're still delayed 10 milliseconds into the waveform, and we're seeing the clock edge 10 milliseconds delayed from our trigger point. And so graphically, here's what we're doing. We have a trigger point, and we're actually looking out here 10 milliseconds delayed. And so if you think about that, we've got 10 milliseconds divided by the 200 nanosecond cycle of the waveform, which means we're delaying about 50,000 cycles into the waveform. Now we're going to apply a little bit of heat. I've got a temperature gun here which has a adjustable temperature control on it. It may get a little bit noisy. So hopefully you can see here the temperature gun is set at 160 degrees F. And what we're going to do is heat up this oscillator circuit, and we're going to count the number of cycles that we see crossing the center point of the waveform, of the display. One, two, 3, 4, 5, 6, 7, 8, 9, 10, 11, looks like we're right about 11 cycles. Now I'm going to remove the heat from the circuit. I'll shut off the temperature gun. And just for kicks, I'm going to hit it with some freeze spray here, and we'll actually see it shift fairly rapidly in the other direction. I'm not going to count these pulses though. Here's the circuit that we're probing, and the ceramic resonator is here in this little metal package just off the tip of the pin. That's the one that I was heating up with the heat gun. So now we're going to do some calculations based on the amount of shift that we saw on the signal. We saw the shift was about 11 cycles. And so the sensitivity of the circuit, if we take those 11 cycles and divide it by the 50,000 cycles that we were delayed into the waveform, and multiply that by 1 million parts per million, we're going to get 220 parts per million sensitivity. But we have to remember that that's over a certain temperature difference. And so my room temperature here was about 67 F, and we raised it to 160 F with the heat gun, and so that comes out to about 71 C minus 20 C roughly, or 50 degrees C is our delta T. So our temperature sensitivity is going to be 220 parts per million over 50 degrees C, or 4.4 parts per million per degree C.